So thank you for inviting me and having the opportunity to talk today. This is probably the longest title of a talk that I've ever received, how we might map network dysfunction in LGS, early developmental changes in the EEG and MRI that portend LGS. So it will be some EEG portion and some MRI portion. And I'm glad with the speaker order because Drs. Gelinas and especially Dr. Archer will actually be much more specific. And I will talk more about networks that we have been mapping and visualizing in particular scenarios, but they are to some degree some concepts that I'd like to share, and then we're going to get much more specific data from the next two speakers. So here we go. So there's my disclosures. So I will be speaking about, let me see why. So I will be speaking about TSC a very little bit, and it is a lesional model disease. Of course, there's a big genetic component with inherent increased epileptogenicity in a combination of abnormal neurons, and probably a big role for glial cells as well. But mainly this is lesional, and some of these lesions are active and some are not. And there's a very high prevalence of infantile spasms. And the emphasis, therefore, is on what we can learn from lesions or lesional epilepsy that causes LGS and LGS-like syndromes. And the emphasis is on tubers, although there are a number of other lesions, and this will not be an exclusive TSC talk, I promise. So again, pretty unique, and this was alluded to early on for TSC, is that there is an opportunity for very early and aggressive intervention, because in utero, you can often see cardiac rhabdomyomas, and you can also, with a prenatal MRI, discover tubers and subependymal nodules and other lesions. So you have the opportunity, because most of these children are not born seizing, to actually see the epilepsy develop and see the concomitant neurological comorbidity emerge. And during this development, we have the opportunity to not only monitor with serial EEG and or MRI, but also to tailor interventions. And for example, here is the seizure frequency, which is quite astonishing. By age 24 months, approximately 85 to up to 90%, historically speaking, will have a first seizure of any type. And you can see that in between month 3 and 9 here, the infantile spasms are very, very steep and then start to flatten a little bit. Focal seizures are more linear trajectory and with a much later onset in some. But the infantile spasms suggests kind of a developmental window during which there is increased vulnerability to this seizure type. And we already talked at length, on epileptic encephalopathies, but the bottom line being that the epilepsy forms an independent contribution to the cognitive and behavioral development of the patient. So this is the way I explain it to my patients. Here's the brain, and the brain is injured or abnormal, resulting in seizures, and it also results in learning and developmental problems, all the way up to cognitive impairment and LGS. And then the seizures form an independent contribution, and the medications may form an additional hit or not, depending on your therapeutic success and your management. And the idea of nipping this in the bud earlier would mean that you can prevent an epileptic encephalopathy by stopping seizures earlier and not needing any of these additional hits, and you would allow the brain for an optimal development given the bad cards that it was dealt. And that is what we're moving to with TSC, and we're not going to discuss the EpiStop trial or the PREVENT trial, but that is what is unique about TSC, but we can learn much more lessons from TSC, as I will show you. So in these serial EEGs that we were doing as part of the TASERN trial, which was a study of 160 patients that were monitored with serial EEGs, first monthly and then bi-monthly, or every 2 months, and that was spaced out as they got older over 5 participating centers. And these EEGs are now being harmonized and stored centrally, so there will be a spectacular database to work on. And you could see that these patients develop not only a seizure focus, but that the focus expands over time. So once the epilepsy emerges, you go from a focal epilepsy here in a patient of 3 months old, a girl that I still follow, and to the same patients at 14 months where the abnormalities are bigger. It's not the best example because you can see some contralateral abnormalities as well. So we go from focal to regional. And I wanted to operate on this girl very early on, but the parents have consistently refused, and I've been unable to convince them. And at 21 months, this is what her EEG looked like. So where we started with a right central focus is now a generous right hemispheric epileptic encephalopathy, perhaps. And so you see a focal expansion of the epileptic network from focal to regional to hemispheric or even global. And this, I think, is a mechanism that the basic scientists maybe tomorrow are going to talk about at length. But I think there is some EEG evidence, at least, for kindling. So do seizures or spikes beget more seizures if they go untreated? And that discussion can extend into electrographic seizures. It can extend into a need for control of seizures. And I think that there's also a use-dependent plasticity going on where progressively more normal tissue gets recruited into the seizure focus. I have not visualized these progressive EEG changes yet over time, but I hope to do that once the data set is more complete. And here is a subset of 40 children of these 160 children that we did serial EEG monitoring on. 2 were lost to follow-up, and 6 were pre-treated with vigabatrin. That was just basically because we were seeing such horrid EEG abnormalities with broad spike and wave complexes, polyspike and wave with overriding fast activity, really a stage that was preceding spasms. And many, 2 were from my site, and several others opted not to wait, despite the fact this was an observational study. So that left 32 infants for a complete analysis, and we looked at features that was predicting the onset of epilepsy and the time in between conversion from a normal EEG to an abnormal EEG. And the 17 of the 38, almost half, had epileptiform activity detected on EEG before the onset of their clinical seizures. And this occurred at an average of about 3 months prior to seizure onset. And there were 3 false negatives, so there was no abnormal EEG, but they developed clinical seizures anyway. That may have to do with the sampling rate or with the duration of the sampling, because this was just regular routine EEGs. And overall, the positive predictive value of an EEG abnormal being followed by clinical seizures within a few months was 77%. And that is more than good enough to work as a very simple, clinically available biomarker of impending epilepsy and TSC. And that is the marker that we're now using to randomize patients in the PREVENT trial to vigabatrin or placebo. So what have we learned from EEGs so far? EEGs predict focal spikes. So I tried to summarize this graphically. And you can see a normal brain and then a small epileptic focus. And that is the time when we have an increased chance of seizures emerging. And we know that if we do not treat or do not treat sufficiently, that these seizure foci may literally grow from local to regional, ultimately to hemispheric or bihemispheric expansion. So it's literally a recruitment of the direct neighborhood into this spike focus. And we can also predict when spasms come on, and this is on a network level. So we analyzed a subset of children in whom at the time we had complete data sets, and this is a bigger number than the 40 that were monitored intensely prior to onset of their epilepsy. So this is both from the TASRN data and from the sub-study, the so-called P20 study. And you can see that in every frequency band, delta, theta, alpha, beta, and gamma, and even high gamma, there is an increased connectivity in pretty much all regions prior to the onset of spasms, as compared to 28 kids here below who did not develop spasms. So this was like normalized data that was cleaned. It was brief moments of sleep, epochs of sleep, and we used a mutual information metric. And it doesn't really, the nice thing about some of these connectivity measures, and also when you use graph theoretical measures, is that they are fairly robust to the connectivity measures chosen. And you can map this out in more detail by, for example, doing graph connectivity measures, graph theoretical measures, such as like clustering coefficient and path length. Basically, these are measures that describe the design of the network. Like, if you have a local connection, what's the chance that two neighboring electrodes are also connected to the other neighboring electrode? And the path length is like, if you go from A to B in the brain, from one end to the other and back, what is on average the number of steps you need to take using only a certain strength of connections, for example. And you can see that these groups are separated somewhat on the basis of these metrics, just like they were separable to some degree on the basis of connectivity. But other than maybe used as a potential biomarker, I think what this tells us is that as a facilitating mechanism, or maybe even as a prerequisite prior to the onset of spasms, you need to have a certain amount of synchronization in order for seizures to be generalized. So intuitively, it makes a lot of sense, and we've been trying to basically quantify these changes prior to the onset of spasms. And indeed, the patient that had spasms had more connectivity. So why am I talking about spasms if they're not the most prominent seizure type in LGS? Well, I think we already spoke about that today, but there is overlap, I'd say ontogenetic overlap even, between spasms and tonic seizures. Here are two EEGs from two vastly different patients, a patient with NKH currently hospitalized right behind me, 3-month-old with really very forcible spasms. And here's a patient, I think discharged by now, 3-year-old with an FGF12 mutation with tonic seizures. And this EEG is a bit messy, but they have the same broad non-localizing spike early on, and then followed by decrement and fast activity. And Dr. Archer later on is going to describe some studies on lesional Lennox-Gastaut and tonic seizures, and the networks that underlie tonic seizures and generalized paroxysmal fast activity. And I think we can learn lessons from spasms as well. And the same, this already came up this morning, the same goes for the slow spike and wave, so typical of LGS here in an 18-year-old with a gunshot wound to the forehead, and ESES here in a 9-year-old girl who had meningoencephalitis and a VP shunt. And we can use these patterns, we can learn lessons from what happened in these other related disorders and figure out what's going on with the underlying networks. Because I think there's overlap between these various forms of epileptic encephalopathy. So West syndrome, CSWS, we already spoke about atypical Rolandics and other related disorders. And here I put a directional arrow into LGS, but seizure type overlap between spasms, tonic seizures, GPFA, and the EEG background. I think there's overlap in many of these, so we can learn lessons from spasms and ESES with regards to LGS, and we can apply some of the same techniques to LGS. So what have we learned from EEG so far? The EEG predicting focal seizures, the expansion of the local epileptogenic focus, but also focal seizures that somehow go from local to global connectivity. But the global connectivity, we do not have a good hub for. We don't know which relays are used in order to generalize this epileptic activity generated by this focus. Again, later on, we'll talk a little bit more specific networks, but we do know that most likely the basal ganglia and possibly the brainstem are involved in this. So that's where we go to the second section of my talk, and that's about MRI and what can we learn from ESCS, for example. So Ivan Sanchez-Fernandez already now nearly 10 years ago described that if the thalamus took a hit in these early injuries, in particular, early congenital abnormalities or soon after birth, that these patients would develop ESCS. And this is very similar to the spasms that we see. We know that in the study from my colleague Harini, we described that structurally acquired lesions, that there was a heavy involvement of the basal ganglia or the thalamus in the subsequent development of spasms. So if you look at lesional spasms, you can, to some degree, find common ground as where these lesions occur. And here is the study that Zach Greenspan was involved in from the neonatal seizure registry. And they also reported in epilepsia that a brainstem injury or deep brain injury in particular was strongly involved with subsequent development of spasms. And so can we actually localize infantile spasms? It doesn't seem to make a lot of sense, but we've already seen that if you have epileptic spasms or infantile spasms or tonic seizures, that you can have a broad mix of injuries. I'm not talking about the genetic epilepsies, but now about the brain malformations, strokes, hypoxic ischemic injury, trauma, brain malformations, and in this case, tumors. And there seems to be no rhyme or reason in which patients develop spasms and which ones don't. And the question is, can we find common ground to how these lesions are distributed? And there's two ways of doing that. One is called voxel-wise lesion symptom mapping, where you basically put all your patients with a certain phenotype, in this case spasms, on top of each other, and you generate a heat map. You put them in a common space, and you generate a heat map of voxels or lesion locations that are affected by certain lesions, and then you will find hotspots. So think, for example, of multiple sclerosis. If you would put all these images on top of each other, you would find Dawson's fingers abutting the corpus callosum. Or you would phenotype people based on an expressive aphasia, and you would find some variety of lesions. But in the end, if you put all the heat maps of right-handed people on top of each other, where their injury is, you would find Broca's in the left inferolateral frontal region. Another way of doing this is with lesion network mapping, and I'm going to explain that to you in a second. But that basically has to do with not asking where the lesions are, but where lesions are connected with, or where they are, what they are talking to. So we did this on 123 patients with TSC, 74 of whom developed infantile spasms, and 49 who did not. And we based this on nearly 170 patients that were enrolled in this study. And 123 of them had good quality imaging. So I thought I had just told you that spasms are generalized, so how can you even localize them? Well, in fact, we know from epilepsy surgery, for example, that spasms can be localized, and there is often a local driver. So spasms can either precede or follow focal seizures, for example, and if you have a MEG or a high-density EEG, you may be able to elicit a focus that you otherwise cannot see. So here from work from Catherine Chu at Mass General, we presented a case where a focal discharge was really readily part of the infantile spasm, and you can localize it to this region, which in an MRI coincided with this cyst-like tuber here, and the patient was spasm-free after surgery. So spasms, now also by as defined by the ILAE, are either generalized or focal, and in fact, in their categorization, classification, they are listed as either focal or generalized. Anyway, so we went back to each subject and we mapped their tubers. In this case, this is just in one plane of one patient, and we would map them in red. We would have a distribution and a volume by lobe. And if you put all the tubers on top of each other in a common space, you can create a heat map of tuber distributions. So this is all the subjects on top of each other. And you can see that it seems to be very random, although I wonder if the motor strip was spared somehow. Here's the patients with infantile spasms, and here's the patients without infantile spasms. And you can see at a quick glance that there doesn't seem to be a major difference in distribution, although perhaps there are more tubers in these subjects. And we found that they were really randomly distributed, and the way that we calculated that is by this Bayesian spatial generalized linear mixed model, which is basically a model that takes into account that if you have one voxel that is occupied by a tuber or defined as being part of a tuber, that you have an increased chance that the voxel right next door is also part of the voxel. So when you do your math on predictability of is there any type of location associated with infantile spasms, then it's good to take into account that the neighboring voxels may also be affected. Otherwise, you have to do an endless amount of correction for false positives. And the best predictive ability of these darker voxels, where apparently there were more tubers, was about 24%. So there's not a single location that could predict which patient would get infantile spasms and who would not. So lesion network mapping is a different way of looking at lesion distributions. And here, for example, are 3 patients with a rare syndrome of very strong visual hallucinations. And I'm blanking on the name of the syndrome. I think it's peduncular hallucinosis. And the phenotype is really well delineated. They're very specific, vivid visual hallucinations, and the patients are easy to describe and to characterize, but then their lesions were disparate. They were not in the same location. For example, here in the mesial pallidum, and here in the upper brainstem or lower midbrain, and then here in the pons. And if you would put these lesions on top of each other in this heat map that we've been talking about, you would find no overlap, yet these patients present exactly the same. But if you project this lesion onto a connectome that is normative, built from 1,000 adults in this case, and you ask what regions is this little lesion connected to, and then there's an inverse correlation with these areas in the back and a positive correlation with these areas. And then the same thing for this one. Which connections does this lesion hit in a normative connectome? So it negatively affects these connections, and it's positively correlated with these locations. And the same thing for the pontine lesion. And then rather than putting the brain lesions in the anatomical space on top of each other, you actually put the lesion network on top of each other. And you can find then where the overlap is on a network level. So it turns out that all these 3 lesions, in this case, there were 23 cases, talk or are connected to these lesions deep in the brain here, this region. So that is what they have in common. They are not anatomically in the same space, but they are all functionally connected to this region. So we did the same thing for infantile spasms, and the tubers were widely distributed. Here's an example. Patient number 1, patient number 2, all the way to patient number 74. And if you put these big lesion maps on top of each other, and you then threshold it and correct it for false detection, then we found that there was a 95% of these tuber distributions were functionally connected to the bilateral globus pallidus the internal globus pallidus, sorry, and the cerebellum vermis, but it was a little less important. And there was no voxels that were functionally connected positively to anywhere. So 71 out of 74 patients had this connection. And when we asked the question the other way around, it gets a bit more technical. But basically we said, okay, in the patient with infantile spasms, are there any locations on a functional connectivity level that are more connected to certain locations as compared to those who do not have spasms? So whereas this method looks into sensitivity, right? 71 out of 74 were connected and were picked up. This one method looks at specificity. And we did this test of conversion and found that these areas in yellow are more connected to the tubers, statistically more connected to tubers in patients with IS than as compared to patients with no infantile spasms. In other words, and the fact that it overlaps with our sensitivity means that these areas are both highly sensitive and highly specific for infantile spasms, in this case in tuberous sclerosis. And then you can chop up the data set in various ways and repeat and even plot an ROC curve. It does not a very strong predictive value, but I think it gave us really a nice insight into pathophysiology of spasms rather than being a real predictor. And you can see that tuber burden also played a role. So if you have more tubers, then you have a higher chance of having infantile spasms. And if you have tubers that are connected to the globus pallidus, then you also have a bigger chance of having spasms. Now the question is, which one is more important? And one way of looking at that is through mediation analysis. And without going into too much detail, but the direct effect from tuber burden on infantile spasms was negligible, not significant. But the tuber burden had its effect, its statistical effect on infantile spasms through connectivity with the globus pallidus. In other words, tuber burden was only important because with more tubers, you have a bigger chance of hitting that same network. So here's my little MRI summary. And what can we learn so far? We know that an injury to the basal ganglia, I'm keeping it purposefully broad, and this includes the thalamus and the deep gray, predisposes to spasms somehow. Here's the focus. There is the influence of an electrical epileptic focus on this hub. And we know that lesions that are functionally connected to the globus pallidus interna, here also represented, but not lesions. So this is a lesion, basal ganglion, and here's the deep gray unlesioned. And if these foci are on the network that connects with the GPI, then you have a bigger chance of spasms. So this tuber theoretically is not contributing to spasmogenesis, if you will. Now, the next question is, can we combine the EEG and the MRI findings to create like a kind of generic low-level model that then hopefully Dr. Archer and Gelinas will take up to the next level in how EEG and MRI may generate spasms. And one way of merging EEG and MRI is by electrical source imaging. And electrical source imaging is a way of creating a solution where you measure the brain waves on the scalp and calculate backwards where the signal has been generated. So you can compare it to perhaps measuring wave patterns on the ocean and then trying to find where the earthquake started somewhere at the bottom of the ocean. And the problem is that it is ill-posed. You have only a handful of electrodes, maybe with high-density EEG you have a few hundred. And there are many more voxels and many more mathematical solutions possible. And for example, here's a dinosaur that falls apart. The researchers later on reconstructed dinosaur and make a perfectly feasible dinosaur, but it's just not correct. So one way to reduce the amount of uncertainty in source localization is by introducing constraints. So you can get more data with higher resolution MRIs and better models. You can get more EEG data, or you can reduce the number of potential candidate regions where seizures are coming from. And that's what we did with so-called lesion-constrained electrical source imaging. So we basically told the computer, rather than saying you can use anywhere in the cortex to put these potential electrical sources as we measured from the brain, we actually said, well, in the case of tuberous sclerosis complex, we know that it's much more likely to be coming from a lesion. So we basically have the lesions compete with one another and say, okay, which of the lesions can best predict as a standalone the electrical activity that we measured on the scalp. And we turn that probability or that ability into a color. And mathematically speaking, tubers that needed much more components and needed much more complex math in order to make this fit would get some kind of punishment and would end up lower on the ranking. So this is what it looks like in practice. So here is a Loretta. It's a distributed source solution where the electrical activity is projected onto the brain, and there's an assumption made on the source. But you can see that the computer is unable to decide whether this is coming from the temporal lobe or from the frontal lobe. And here in black is a resection cavity that I colored in a patient who then became seizure-free. And we know that there was a tuber there. Now, if I tell the computer there are 2 tubers here and there's 1 tuber there, and you can only put the solution in one of the lesions, the computer ultimately says, okay, fine, the best match is this area, and this one overlaps with the surgical cavity in a patient who subsequently became seizure-free. So therefore, we're forcing the model to think in boxes and therefore help us make decisions visually at least, on which tubers are more likely to be epileptogenic. Here's another example of a tuber that fell smack in the resection cavity that, based on the surface EEG, was indeed the hottest tuber. And here, same thing. So why am I saying that? Because I think the next question is not which of the tubers or which of the lesions is lying, is part of this spasmogenic network or is connected to the GPI in my research. But I think that the lesions have to be active, because we know that the seizures and the seizure foci that cause spasms are active regions, as I was talking before about the mix between spasms and focal seizures. So here's how I put the whole picture together. And this is really speculative, so I hope I'm not too far out there. But your EEG is clean, then you develop focal seizures. If the volume of irritation towards this hub overcomes whatever inhibition the central hub was doing, then you can get spasms. And if there's a lot, then maybe it is refractory spasms. Or if you have focal seizures because there's only one focus and this gating mechanism does its work. But if there's 2 foci, that may be enough to overcome the central inhibition, for example, GABAergic inhibition in GPI. And if there's a lot of foci that are all part of this network, because again, this one, for example, is not contributing, then maybe the spasms are harder to treat. And if you have a lesion in this gating mechanism or this gatekeeper mechanism, then you can get earlier spasms and so on, with more irritability of this focus, refractory spasms. And if you have a lot of epileptogenic volume that projects onto this central gray, then perhaps you have more than just refractory spasms and it's just impossible to fix. So things that I would think for Lennox-Gastaut more specifically would be very interesting would be to apply lesion network mapping to tonic seizures or to GPFA in lesional Lennox-Gastaut. So I would love to have access to Dr. Archer's lesional LGS cases and explore spasms, for example, in perinatal strokes, refining some of these methods to, rather than to have a pattern of lesions that are connected to GPI, see if you can highlight just 1 or 2 candidate lesions, or if somebody has a really large abnormality, maybe we can find out within a critical region, which within a large, let's say, hemispheric malformation, can we identify areas that are contributing more or most to spasms or tonic seizures. And there's some technical stuff that I need to do, but the question is, if you have a dominant or strong epileptogenic focus, I would predict that to be part of that network. And ultimately, what this work could lead to would be to target either a lesion or part of the lesion if you can identify it reliably with both MRI and EEG, or if not, you should be able to target the network. And so that's where I'm hoping the field is going. Thank you.